Hello friends, myself Ashok Bagda from Dr. Subhash Technical Campus, and today we are going to discuss about logarithmic decrement from the subject Dynamics of Machinery. So let us start. So first of all, we have already discussed about underdamped system. So we know that in underdamped system having cyclic motion, or we can say that it is underdamped system is a periodic motion. But the rate of in an underdamped system, the amplitude of vibration is continuously decreased with respect to a time. So here we are going to discuss about logarithmic decrement. It is denoted as a delta. So delta is a logarithmic decrement. So first of all, let us understand what is a logarithmic decrement. The rate of decay of amplitude is measured by the parameter known as a logarithmic decrement. That means by which amount the amplitude is decreasing in every cycle. So if we see the figure, so this is first cycle, this is another cycle, this is third cycle. So in every cycle the amplitude of vibration is decreasing. So the rate of decay of amplitude is measured by the parameter known as the logarithmic decrement. The rate of decay of amplitude is proportional to the amount of damping present in the system. My dear friends, we have already discussed about a simple pendulum. We know that in a simple pendulum, if we displace the mass attached at the string, then our pendulum is continuously oscillate in a to and fro motion about its mean position. But after some period of time, our pendulum will come in an equilibrium condition. Why? Because there is a air is present, there is a pivoted friction is present. So because of this damping, so there is a air as a damper. So because of the air damping, our pendulum will come in equilibrium condition. So here the amplitude is decreasing of the vibration. Amplitude of vibration is decreasing because of the damping. So if a system having some damper is present, then we can say that the amplitude of vibration is continuously decreased. But the rate of decay of amplitude is proportional to the amount of damping present. Thus, so the larger damping, the greater will be a rate of decay. So we can say that if damping is large, then we can say that there is a large decrement in amplitude. So let us see the definition of logarithmic decrement is defined as the natural logarithm of the ratio of any two successive amplitude on the same side of mean position. Again we can say that logarithmic decrement is defined as the natural logarithm of the ratio of any two successive amplitude on the same side of mean position. So here this is the graph for a displacement versus time. So x1 is the amplitude in a first cycle and x2 is the amplitude in a second cycle. So we have to consider any two cycle. So we can say that log x1 upon x2, the ratio of any two successive amplitudes. So if we consider x1 and x2, so log x1 upon x2 is known as a logarithmic decrement. So let A and B, so we consider two position. This is A position and B position. So let A and B corresponding points on the successive cycles where displacement is maximum. So we can say that periodic time Tp is equal to the periodic time. Periodic time means it is a time required to complete one cycle. So A and B is a one cycle. So this is one cycle. So periodic time we can say that is equal to T2 minus T1. But periodic time, it is a underdamped system. So we can say that the amplitude of vibration is continuously decreased. So in another way we can say that periodic time it is also rewritten as 2 pi upon omega d. So where omega d is a frequency of damped vibration. But so we rewrite this equation Tp is equal to 2 pi upon omega d is equal to omega n into bracket 1 minus zeta square. It is damped vibration. So omega d is equal to, we can say that in a bracket 1 minus zeta square bracket square into omega n. Now the amplitudes at time t and t1 and t2. So amplitude at time t1 and t2 are, so x1 is equal to, we can say that x into here, x into e raised to minus zeta omega n t1 into sine in bracket omega d t1 plus phi bracket complete. So this is a theta. So theta is omega d t1 plus phi. Similarly, x2 is equal to x into e raised to zeta omega n t2 into sine omega d t2 plus phi. Now, if we put the value of t2, so t2 is equal to t1 plus tp. So here we get x into e raised to minus zeta omega n in bracket t1 plus tp into sine in a whole bracket omega d in a bracket t1 plus t2 bracket complete plus phi whole bracket complete. So if we simplify, then we get x into e raised to minus zeta omega n in bracket t1 plus tp bracket complete into sine bracket omega d t1 plus 2 pi plus phi bracket complete. So sine this one, the solution of this one is, if we simplify, so we get sine omega d t1 plus phi. So x2 we get x into e raised to minus zeta omega n t1 plus tp into sine omega d t1 plus phi. So if we take x1 upon x2, so if we put the value of x1 and x2, then we get e raised to minus zeta omega n in a bracket t1 minus tp. So we get x1 upon x2 is equal to e raised to zeta omega n tp. Now according to the definition of logarithmic decrement, delta is equal to log in bracket x1 upon x2. If we put the value, so delta is equal to, we can say that log e raised to zeta omega n tp. So finally we get delta is equal to zeta omega n tp. Again we rewrite zeta omega n and tp is equal to 2 pi upon omega d. So delta is equal to zeta omega n into 2 pi upon in a root 1 minus zeta square into omega n. So we get delta is equal to 2 pi zeta under root 1 minus zeta square. So this is the equation of logarithmic decrement. Delta is equal to 2 pi zeta upon root 1 minus zeta square. The logarithmic decrement can be also determined as follow. We know that delta is equal to log x0 upon x1, because x0 is a initial displacement and x1 is a displacement in first cycle. Similarly, the delta is also equal to log x1 upon x2. Similarly, it is also equal to x2 upon x3. Similarly, we can rewrite is equal to log xn minus 1 upon xn, because delta is same for every period of cycle. So in a general way, we can, if we write in another way, so n delta is equal to log x0 upon x1 plus log x1 upon x2 plus log x2 upon x3 plus log xn minus 1 upon xn. So if we simplify this one by using rules of log, then we rewrite this equation in this way: log x0 upon x1 into x1 upon x2 into x2 upon x3 into and xn minus 1 into xn. So finally we get n delta is equal to log x0 upon xn. So delta is equal to, we can say that 1 upon n log x0 upon xn. So where x0 is the amplitude at starting position and xn is the amplitude at after n cycles. So this is another equation: delta is equal to 1 upon n into log x0 minus xn. Now let us see an example for the logarithmic decrement. An underdamped shock absorber is to be designed for a motorcycle of mass 250 kg, such that during the road bump, the damp period of vibration is limited to 3 seconds and amplitude of vibration should be reduced to 1/18th in one cycle. My dear friends, in our bike, we know that in a suspension system there is a damper is present, and because of this damper, the dampers are used to reduce the frequency of vibration, or we can say that reduce the amplitude of vibration. So here, and find first the stiffness of spring required, and second the damping coefficient of shock absorber. So in this case we have to determine stiffness of spring and damping coefficient of shock absorber, that means C. Here the mass of motorcycle is m is given 250 kg and time period of vibration, that means the damp period of vibration is limited to 3 seconds. So time period Tp is given 3 seconds. So logarithmic decrement, we know that, let us assume x0 is initial displacement. Let us assume x0 is initial amplitude and x1 is amplitude after one complete oscillation. So here the damp period of vibration is limited to 3 seconds and the amplitude of vibration should be reduced 1/18th in one cycle. That means if we consider x1, so it is the initial x1, the amplitude of first cycle is equal to the amplitude of initial cycle divided by 18th. So we rewrite this equation, x0 upon x1 is equal to 18. So logarithmic decrement is given by delta is equal to 1 upon n into log x0 upon x1. So here 1 n is equal to given 1 cycle. So log x0 upon x1. So we get delta is equal to log 18. So delta is equal to 2.89. Now damping factor, we know that damping factor delta is equal to 2 pi zeta under root 1 minus zeta square. So if we simplify this equation, then we can rewrite zeta is equal to delta. Zeta is equal to delta divided by 4 pi square plus delta square. If we put the value of delta, then we obtain zeta, damping factor zeta is equal to 0.4178. Now stiffness of spring. The natural circular frequency of damp vibration is omega d is equal to 2 pi upon Tp. Now time period is given 3 seconds, so we write 2 pi upon 3, so omega d is equal to 2.09 radian per second. Now omega d is known, so we can calculate omega n. So omega d is equal to omega n into root 1 minus zeta square. So if we put the value, then we get omega n is equal to 2.30 radian per second. Now omega n is a natural frequency, so is equal to root k by m. So if we put the value of natural frequency 2.30 is equal to root k by 250, because m is mass of bike is 250. So we get k is equal to 1322.52 Newton per meter. So we obtain k. Now damping coefficient zeta is equal to c by cc. We know that. So we have value zeta is equal to c by 2m omega n, because cc is equal to 2m omega n. If we put the value of c and m, then if we put the value of zeta and omega n m, then we get c is equal to 480.47 Newton into second per meter. I hope you understand about the logarithmic decrement. Thank you.
Hello friends, welcome in a lecture of Dynamics of Machinery subject. Myself Mitesh Patel, I am an assistant professor in a mechanical department at a Dr. Subhash Technical campus. Today's our lecture topic is a logarithmic decrement. In this lecture we discuss about we solve the numericals of logarithmic decrement. Okay, so let's start the lecture. Now first we know that what is the logarithmic decrement. Means in the damp vibration the amplitude is reduced, or vibration amplitude is decreased with respect to time. So decrement of amplitude in one cycle or two cycle or any number of cycle is find out with the help of logarithmic. So it's called the logarithmic decrement, and logarithmic decrement is defined by the delta. Okay, so logarithmic decrement is find out for the one cycle, two cycle, three cycle, four cycle, and any number of cycle. Okay, let's start to solve the first example. So first see the what kind of data is given in the example. See that damped vibration system, the mass having 20 kg, mass is given 20 kg, makes 40 oscillation in 25 seconds. Okay, the oscillation is given 40 oscillation and the time taken to 40 oscillation is a 25 seconds. So T is given and capital N, it's a number of oscillations, N is a 40 and time T 25 second. Okay, the amplitude of natural vibration decreased to 1/8 of the initial value after 8 oscillation. When the 8 oscillation is complete, the value of amplitude is reduced from the initial value is of 1/8. Okay, 8 times reduce the value of amplitude than the initial value. Okay, now what value of determines? The first one is the logarithmic decrement, damping factor, damping coefficient, and spring stiffness. The fourth value is find out. First we find out the logarithmic decrement. So we know that how to mathematically find out the logarithmic decrement. Delta is equal to 1 upon n log e natural log x0 upon xn. x0 is the initial value amplitude and xn is the n number of cycle. If we have to find out the for a one cycle logarithmic decrement for a one cycle, then here x0 is the initial amplitude and xn is a n number of cycle and n is a 1 for a one cycle. So x0 upon x1. If we have find out the logarithmic decrement for a two cycle, then x0 upon x2. If we have find out the logarithmic decrement for a continuously 4 cycle, then x0 upon x4. Here we find out the logarithmic decrement for a 8 oscillations or 8 cycle. So x0 upon x8 and n is a number of cycle is a 8. So here n is a 8, 1 upon 8 and x0 upon x8. Okay, now we have to value of x0 and x8, then we have find out the delta. So here the conditions is given. The x8 is the amplitude of 8th cycle and x0 is the amplitude of initial cycle. Okay, as shown in figure, x0 is the initial amplitude of initial cycle and x8 is a x8 amplitude or amplitude of a 8th cycle. Okay, as shown in figure. Now the relation is given that the 8th cycle amplitude is 8 times reduce of initial amplitude. So x8 is equal to x0 by 8. Okay, now here the ratio is x0 upon x8. It's developed by this relation. X0 upon x8 is equal to 8. So put the value of this relation 8 and now we have a value of all elements and we find out the value of delta logarithmic decrement 0.2599. Okay, meter for a 8 cycle. After 8 cycle, the decrement of amplitude from initial to 8 is a 0.2599. Okay, now find out the damping factor. Okay, so damping factor is equal to damping coefficient to critical damp coefficient. We initially know that, but here the damping coefficient is also find out. So damping factor is find out with the logarithmic decrement delta. Okay, so mathematical relation between the zeta and damping factor is shown in slide. Is the zeta is equal to delta upon under root 4 pi square plus delta square. Okay, so here the value of delta logarithmic decrement we already find out. So zeta is the value of zeta we can find and the final value of zeta is a 0.0409. Okay, The zeta unit is a unitless number because the ratio of damping coefficient. Okay. Now we have to find out the damping coefficient or stiffness. So here we know that from the zeta is a ratio of damping coefficient to critical damp coefficient, and here we find out the damping coefficient. Here for that we have to find out the value of zeta, and we already find out. So we have to find out the critical damp coefficient, and critical damping coefficient is find out by 2m omega n. Okay, so omega n we have to find out. M is given 20 kg, but omega n is find out for that case, and we know that the omega n for a spring mass system is find out with the relation under root k upon m. So but the k is not given for that example. So first we have to find out the stiffness, but the m is given. So first find out the stiffness of spring for this particular example. So if we know the value of omega n and m, then we find out the value of stiffness. So first find out the value of omega n, and omega n value is find out with the help of omega d equation. Omega d is a damped circular frequency and omega n is a natural circular frequency. So omega d and omega n relation is as shown in equation. Omega d is equal to omega n under root 1 minus zeta square. Okay. Now zeta's value is know that we already find out, but we don't have a omega n value and omega d value. Okay. So first we have to find out the value of omega d. Here the damping vibration is there and frequency is given. The number of cycle per unit time, it's called the frequency. So we have a frequency, value of frequency find out from the conditions and data given into the example, and from that we know that according to frequency omega upon 2 pi. From this relation we find out the value of omega d. Here the omega is omega d because the damped free vibration is there. So first of all find out the frequency for a damped vibration. So here 40 cycles complete in a 25 seconds. So 40 upon 25 we find out the frequency 1.6 Hz for a damped vibration. Now from the equation of frequency omega d upon 2 pi, so omega d is equal to frequency into 2 pi. So here the value of fd is put and pi put the both value, and we find out the finally omega d 10.0.5 radian per second. And now the value of circular damped frequency omega d is put in this equation and find the value of natural circular frequency 10.09 radian per second, and this value is of omega n is put in this equation, and finally we get the value of stiffness k. Okay, and stiffness value is find out 2039.27 Newton per meter. Okay, now remaining one is a damping coefficient. We have to find out the damping coefficient. So omega n value is now known 10.09 radian per second. So put the value of in this equation of omega n and find the value of damping. Zeta value is there already, we find out first. So damping coefficient value is find, and it's a 16.50 Newton into second per meter, and all the non-known values we find out and solve the example. Okay, now take the another one. A mass suspended from a helical spring vibrate in viscous fluid medium whose resistance vary directly with the speed. Okay, it is observed that the frequency of damped vibration is a 120 120 per minute. Okay, and the amplitude decrease to 20% of the initial value in one complete cycle. Find the frequency of free underdamped vibration of the system. So we have to find out the frequency f. Okay, finally, according to conditions, the value is given is a 120 reduction in amplitude per minute. So per second, per 60 second, 120 meter is reduction. So FD is equal to 120 per 60. So we find out the frequency 2 Hertz. Okay. Now we have to find the frequency f. So we have to find out the value of omega n first, and omega n find out with the value of equation of omega d, and from that we can find out, and fd value is already find out. Okay, it's a 2, and we find out the value of omega d, and then we have to find out the value of omega n, but we have to find out the value of zeta. Omega d value is already find out, 12.56 radian per second. Okay, so we first find out the zeta value, and we know that the value of zeta is find out with the help of damping coefficient or logarithmic decrement delta. Here the damping coefficient is not given, so we have to find out from this equation damping factor is find out. So first we have to find out the value of delta, and delta is a logarithmic decrement, so we know that the delta is equal to 1 upon natural logarithm x0 upon xn. Now here the condition is given, the amplitude is decreased 20% of initial value in one complete cycle. So here the value is a convert a percentage in a value is a 0.2 value. Okay, is decreased, 0.2 value is decreased in amplitude in a one complete cycle. So x0 to x1, so x1 amplitude is decreased by 0.2 times, then x1 is equal to x0, x1 is equal to x0 by 0.2. Okay, so x0 upon x1 is equal to 1 upon 0.2. Okay, so here the ratio is put, ratio value is enter in this equation and find the value of delta. Okay, and now we find out the value of delta. This value is enter into this equation zeta, and we find out the value of zeta. Okay, now this zeta value is put into the equation of omega d, and we find out the value of omega n 12 into 96 radian per second, and this value of omega n is put in the natural frequency equation, and we find out the value of natural frequency. Here the natural frequency equation, the omega n is taken because we have to find the frequency of free undamped vibrations. Undamped vibration is called the natural frequency of undamped vibration. So its a natural frequency is a omega n. If we say that we find out the natural frequency of damped vibration, then here omega is a omega d. Okay, so here undamped vibrations, in undamped vibration the frequency is considered the omega n, and we finally find out the natural frequency is a 2.06 hertz. Okay, the another example is taken, and what data is given. Let's see, the machine of 75 kg, mass is given 75 kg, is mounted on the spring. It's having a stiffness 10 Newton per mm, stiffness is given 10 Newton per mm, is fitted with a dashboard to damp out the vibration during vibration, is found that the amplitude of vibration dimensions from 40 mm to 6 in 2 cycle. Okay. In 2 cycle, the amplitude is decreased from 40 mm to 6 mm. Okay. So x0 amplitude value is a 40 mm, and after 2 cycle, after 2 cycle after 2 cycle, amplitude is a x2 is a 6 mm. Number of cycle is a 2, so n is equal to 2. Now we have to determine the resistance of despot at a unit velocity. So we have to resistance first, find out the resistance first. Frequency ratio of damped vibration to undamped vibration means we have to find out the ratio of damped vibration to undamped vibration means omega d upon omega n. This ratio we have to find out. And then time period of damped vibration Tp. Okay. So first we have to find out the equivalent stiffness, because here given a 3 spring, okay, and each having a stiffness 10 Newton per mm. So all these 3 springs combined stiffness we have to find out is called the equivalent stiffness. And here the spring is connected in a parallel connection, parallelly connected, this 3 spring. So equivalent stiffness is find out with the K is equal to K1 plus K2 plus K3. So 10 plus 10 plus 10 is equal to 30 Newton per mm. So it is the equivalent stiffness, 30 into 10 raised to 3 Newton in per meter. Okay. Now we have to find out the omega n natural circular frequency, because of the we have to also find out the ratio of omega d upon omega n. So we also find out the omega d, but here we know that the omega n we find out with the K upon m in a spring mass system. So K is also given, m is also given, so omega n is find out under root K upon m, and it's a 20 radian per second omega n. Now we also find out the logarithmic decrement to find out the value of zeta. So delta is equal to 1 upon n log e upon natural logarithm into x0 upon xn. Here according to data for a 2 cycle, so x0 upon x2 logarithmic decrement is find out for a 2 cycle, so x0 upon x2, and x0's value is a 40 mm and x2's value is a 6 mm. Here the value of displacement ratio, so we can take the units in mm also and takes the units in meter also, so nothing to difference in unit because the unit is cancelled. So now n is equal to 2 because the 2 cycle is considered. So logarithmic decrement is find out is a 0.9485. Now according to logarithmic decrement we find out the value of zeta from this equation, and its value of zeta is a 0.1492. Okay. Now we find out the damping coefficient. Let's define the required resistance of despot at a unit velocity. Okay, at a unit velocity. Okay, so damping coefficient is defined as the force per unit velocity. Okay, see from the unit of damping coefficient. So first value we have to find out in this equation is a damping coefficient. It's defined the resistance force per unit velocity. So according to damping coefficient we find out from the zeta's equation. So zeta is already find out. We have to find out the zeta. We have a zeta damping coefficient, and zeta value is already find out, so we have a value of zeta, and also find out the value of cc, and cc is find out with the help of 2 m omega n. M value is given and omega n value is already find out. So put the value of omega n zeta. So we find out the value of C, and it's the resistance force of despot at a unit velocity. Okay, it's 447.80 Newton into second per meter. Now we find out the ratio of omega d upon omega n. Omega n is already find out, value is omega n is at 20 radian per second, and now we have to find out the omega d, natural damped circular frequency omega d, and its equation is omega d is equal to omega n under root 1 minus zeta square. Zeta's value is also there. Omega n is omega n value. Put the value of both and we find out the value of omega d is 19.77 radian per second. So take the ratio of omega d upon omega n value, and finally the ratio is 0.9888. Now the last one is the time period. So here we know that from the circular frequency equation is omega is equal to 2 pi upon t. So here the damped vibration is there, so omega d and time period Tp. So we have to find out the time period Tp. So Tp is equal to 2 pi upon omega d, and here we have a value of omega d. So enter that the value of omega d, and we finally find out the time period value 0.3178 second. Okay. Now the example is complete. So this way you have to solve you easily solve the example of logarithmic decrement. So in this example the value of find out is given into the example is zeta, natural circular frequency omega n, damped circular frequency omega d, okay, and the value of zeta and the value of damping coefficient, time period. Okay, so you very well know the now equation how to find out the omega d, omega n, zeta, damping coefficient. Okay, all the relations you have to know now, and also the relation of delta, it is a logarithmic decrement, and between a zeta and logarithmic decrement mathematical equation according to logarithm equation. So now you can easily solve the example of logarithmic decrement. I hope that. Okay, so thank you for listening or watching the video of this lecture. Okay, thank you again.